Right, so hello everyone, welcome to fifth week's tutorial session of AAAT, State Space Approach to Control System Analysis and Design. I am Sushi Siddharth and I'm a TA for this course. So let's begin by recalling the concepts from week 5. Alright, we'll begin by recording equilibrium points and how to find equilibrium points for a nonlinear system. Talk about positive and negative definiteness and semi-definiteness. Then we'll talk about stability. So, Lyapunov function-based stability, which will talk about this nonlinear system being stable. The nonlinear system being asymptotically stable. And globally asymptotically stable. We'll also talk about marginal stability. So let's begin. So given a nonlinear system, x dot equals f of x. So the system would have equilibrium points, and we can compute this by getting x dot equals 0. That is finding the roots to this equation. Alright, so let's look at the question. The system is x1 dot equals uh, minus x1 plus 2x1 cube plus x2 and x2 dot equals minus x1 minus x2. So this can be written as x1 dot x2 dot equals 1 of x1 x2 and f2 of x1 x2. Equilibrium point will be the solution to the equations f1 x1 x2 equals 0 and okay, so let's find the solutions. So let's begin with the second function. As 1. And from the first equation, we have minus x1 plus 2x1 cubed plus x2 equals 0. Let's substitute x1 equals minus x2 in this equation. So we would get x2 minus 2x2 cubed plus x2. Okay, so this means that we have 2x2 minus 2x2 cubed equals 0. X2 times 1 minus x2 square equals 0. And the solution for this equation are x2 equals 0 and 1 minus x2 square equals 0. Which implies that x2 could be plus minus 1. So x2 would be 0, 1 and minus 1. Therefore, x1 is going to be 0, minus 1 and 1. So the system has multiple equilibrium points. Which are 0, 0, minus 1, 1, 1, minus 1. Alright, so I hope that this question was clear to you. Let's move on to determining positive and negative definiteness of two functions. So let's recall the definitions before we move on to the question. So we are looking at functions like v of x equals transpose qx, where q is for a function like this. Just a second. So for a function like this, Vx is positive definite if Vx is greater than 0 for x non-zero and Vx equals 0. So this is implies that Vx is positive definite or Q is positive definite. The general definition for positive definiteness. For semi-definiteness, it is Vx greater than equal to 0. for x non-zero. Right. So positive is semi-definitely Ax is greater than or equal to 0 for non-zero x. And of course, we have that which is 0. So the positive semi-definite is Dx can be greater than or equal to 0 for x which is non-zero. So if not the case for positive definite. So it's only this. We have similar inequalities for negative definiteness. So Dx is less than 0 for non-zero x. This is negative definiteness. And similarly, we have negative semi-definiteness. So let's look at a few examples. Let this x1 squared plus x2 squared. So in this case, x means it's a two-dimensional statement. Alright, so it is greater than, so at 0, it is exactly 0. And for any non-zero values of x1 or x2, it is always greater than 0. Right? So this means that x1 non-zero and x2 non-zero. So this means that Vx is positive definite. So that is example. Vx is x1 plus x2 whole square. So at 0, it is 0. At x1 equals minus 1 and x2 equals 1, we have 0. Right? So Vx is 0 for non-zero x. And Vx is always also positive because it's a square term. So this means that Vx is greater than or equal to 0 for non-zero x. This implies that Vx is positive semi-definite. So that Vx equals minus x1 squared minus x1 plus x2 squared. So let's expand the second term. This would help us in determining the definiteness. Or we could just do just apply a square minus b square here. A square is minus x1 square and b square is x1 plus x2 square. Let's see if we can do this. Mm, or maybe let's just try first for substituting zero. So we add zero is zero. So b x is minus x1 squared plus x1 plus x2 squared. So bx is always going to be negative. We have to check if it's also zero at some non-zero point x. So that's not the case, right? Let's try x1 equals 0, so that the first term is 0. And for the second term to be 0, x2 has to be 0. So this implies that Vx is always negative for non-zeros. This implies that Vx is negative definitely. Just let's take an as example. Vx is x1 x2 plus x2 squared. So V at 0 is 0. That the term x1 x2 could be positive or negative or 0, and it could also be greater than or less than x2 squared, right? So x1 x2 can be 0 or greater than 0 or negative, and x1 x2 can be. So this means that Vx could either be positive. This means that Vx could be positive or negative. This implies that Vx is indifferent. That is, you cannot comment on whether it is positive definite or negative definite. Alright, so I hope that this was clear to you. Now let's look at the question. Consider Vx equal to ax1 squared. So let's first write this down in the quadratic form. So Vx can be written as X can be written as x1, x2, x3, a01, 080, 1, and 3. So this means that we have this as Q, or this is P. And now we have Vx series X transpose Px. Okay, so to comment on the definiteness of Vx, we need to comment on the definiteness of the matrix P. So let's just check if P is symmetric first. P transposes A01, 082, and 2. This is equal to P. Alright, so now we can comment on the definiteness of P. To do that, we need to write down the principal uh, minors of P, the leading principal minors. What are they? This is one, then the second one, and the third one is the determinant of the whole matrix. So R A, then A square. Then we have uh, this relationship. A times A square minus 4 plus 1 times minus 8. So this is A cube minus 4A minus A. No. So this and this are the leading principal minors of P. Okay, so Vx is positive definite if all of the principal minors of P are positive, right? So A should be greater than 0, A square should be greater than 0, and A square minus 5 should be greater than 0. So this means that A should be greater than 0 and A square minus 5 should be greater than. A should be greater than plus minus root 5, but since A is greater than 0, therefore A should be greater than root 5. So this and this. Alright, now for negative definiteness, the leading principal minus P should be positive. So what does this imply? Minus p would be a 0 minus 1, 0 minus a minus 2, minus 1 minus 2 minus a. So leading principal minus are a. This should be greater than 0, which implies that a should be less than 0. Then we have a square should be greater than 0. And finally, the determinant of minus p, right? So this is determinant of minus p. Square minus 4 minus 1 minus 8 minus 3 plus 4a minus a times a square minus 5. So this should be positive. So this implies that minus a should be positive, which we already have from the first inequality. And a square minus 5 should be positive. Mm, let me see. So a square should be greater than 5. Let me check if this is correct. First of all, a is greater than 0, which is incorrect because we have that a should be less than 0. So for this to be true, we have uh, 5 minus a square should be less than 0. Okay, let's see what we get. So see, this implies that a should be minus under root 5. Okay. So this means that Vx is positive definite for a greater than under root 5, negative definite for a less than under root 5 minus 5, and indefinite in this interval. Just let me check this one for a second. Okay, so let's write this. And this would clarify the negative, the condition of A for negative. The even numbered minus being positive. So this implies that they should be less than minus. Okay. Let's talk about stability, stability and global asymptotic stability based on the Lyapunov function analysis. Alright, so let's say that we have a non-linear system, x equal to x, and x0 is an equilibrium. So for this system, we define a Lyapunov function Vx, and the conditions are that V at 0 should be 0, Vx should be positive otherwise. So let's say that V is defined from a domain Rn to R. So Rn for states x1 to xn. So Vx is greater than 0 otherwise. That is for non-zero x. And V dot x is less than equal to 0 in 0. implies that the origin is stable. If you are also able to prove that Vx is less than 0 for all x in D except the equilibrium, then x equals 0 is asymptotically stable. Okay, so this is stable, this is asymptotically stable. And for global asymptotic stability, we have, so these are the conditions that V at 0 should be 0, Vx should be greater than 0 for all non-zero x. Since we are talking about global asymptotic stability, V is defined from Rn to R and not a certain D of R. Okay. So this is one. Second condition is that if the limit of norm x tends to infinity, this implies that Vx should also tend to infinity. And the third condition is that V dot at x should be less than 0 for all non-zero x. So in RLA, not V. So if all of these three conditions are satisfied, then x equals 0 is globally asymptotically stable. Alright, so let's consider the question. X2 dot is minus x2 minus a x1 squared, where a is a scalar and it is positive. Also consider a Lyapunov function. V of x1 comma x2. So you can either write v of x or v of x1 comma x2. And this is given by x1 squared plus 2x2 squared. So first let's see if the first condition is satisfied, which is positive definiteness of V. So V at 0 is 0, 0 is 0, and V at any x1, x2 is always positive. Because it's squared of x1 and x2, right? For x1 non-zero, x2 non-zero. Therefore, V x1, x2 is positive definite. Now let's compute V dot. So we'll use chain rule. This is del V by del x1 times x1 dot plus del V by del x2 x2 dot. So this is 2x1 x1 dot plus 4x2 x to 1. Now let's substitute the dynamics from 1 and 2. Okay, so this is plus 4 x2 minus x2 minus a x1 square. So this means we have minus 2x1 square plus 2x1 x2 square. Mm. Okay, so you can see that these are square terms with negative signs, but these can be positive or negative depending on x1 and x2. So are negative, sign indefinite, again sign indefinite. Alright, so let's see if we can simplify this expression. And this would be minus 2x1 squared, 1 minus 2ax2. So I've combined the first and the last term. Similarly, we have minus 2x2 squared, 2 minus 2x1. So this is b dot. Now we have to prove asymptotic stability. So b dot should be less than 0 for non-zero x. So observe that we already have negative signs here. So for v dot to be negative, 1 minus 2ax2 should be positive and 2 minus 2x1 should be positive. So observe that we are talking about asymptotic stability and not global asymptotic stability. So these two inequalities help us to define the region D in which V dot is negative. So let's see. This one implies 2ax2 is less than 1, which implies x2 is less than 1 by 2a. This implies 2x1 is, sorry, there should be a somewhere. So this is 2ax1. 2ax1 has to be less than 2, which implies x1 has to be less than 1 by 8. So let's plot this on the x1, x2 plane. Let me see. Let's just so a is positive, so 1 by a is going to be positive, and x1 should be less than 1 by a. So x1 is allowed to lie on the left hand side of a, and x2 should be less than 1 upon 2a. So this means x2 has to lie below 1 by 2. So let's define a region D. D can be, so this is based on your choice. Let's define minus 1 by a here, minus 1 by 2a. So for x1 lying in minus 1 by 8, 1 by 8, and x2 lying in minus 1 by 2, 8, 1 by 2, 8. V dot is strictly 0 for x non-zero. So in D is all the points x1, x2 such that x1 lies in this interval, x2 lies in. Therefore, x equals 0 is asymptotically stable. Okay, so let me know if you have any doubts regarding this question, and then we can move on to the next one. So if there are no doubts, on the next question. Question number 4. Alright. So let's begin with part A. So first is positive definiteness of V. So Vx is V at 0 is exactly 0, and Vx is greater than 0 otherwise. So this implies that Vx is positive definite. So you can just write that Vx is greater than 0. So this means that Vx is positive definite. Okay, now let's compute V dot. So what is del V by del x1? Mm, So this is 2x1, 1 plus x1 squared. This is 2x1 plus 2x1 cube minus 2x1 cube. So cancel these and get 2x1 over 1 plus x1 squared whole square. Del d by del x2 is simple. It is simply 2x2. So let's write that v dot x. Substitute the dynamics. So this is 2x1 plus x1 squared plus 2x2 minus 2 x1 plus x2 and 1 plus x1 squared. So let's just write down in terms of du because those are positive terms. So now let's expand these terms. So this is minus 12 x1 squared plus 4 x1 x2 by u squared. Then we have minus 4 x1 x2 u squared minus 4 x2 squared u squared. So these terms get cancelled and we have minus 12 x1 squared by u4 minus 4. Okay, so this is going to be less than 0 for x1 non-zero, x2 non-zero. Right? Because we have negative signs here and the variables have positive parts, actually even powers. So this is squared, and we have e to the power 4 and e to the power 2. Okay. So we have v dot x is negative for all x in R2 except 0. This is R2 minus 0. This 0 is in R2 also, right? This is 0, 0. Okay, so we have proved part A. This is done. And now we have to show that the origin is not, not globally asymptotically stable. This implies that origin is asymptotically stable. And in part B, we have to prove that it's not global. So let's recall the requirements for global asymptotic stability. That for Vx should be positive definite, V dot x should be negative definite, and if norm x tends to infinity, then this implies that Vx should tend to infinity. So norm x is the Euclidean norm, which is x1 squared plus x2 squared. square. So this goes to infinity in three cases, right? Either x1 goes to infinity, x2 goes to infinity, or both of them tend to infinity. So Vx is uh, x1 squared as x2 tends to infinity, Vx also tends to infinity. However, if x1 tends to infinity, then we get uh, limit x1 tends to infinity plus some constancy, right? This is so divide by x1 square in the numerator and denominator. Which means that v of x does not tend to infinity. Therefore, x equals 0 is not globally asymptotically stable. Okay. So I'll pause for a second and then we'll move on to the next question. If you have any doubts, please let me know. Let's move on to the next question. So the nonlinear system is x1 dot x2 dot so to linearize the system, let's say this is f1 x1 x2. The linear system would be, I'm denoting the matrix as A. This is del f1 by del x1. This is the Jacobian. Is evaluated at the origin. So let's compute this. This is going to be minus 1 plus this is x2 squared plus 3x1 squared. And this is x1 x2. And we have cos x1 and then minus 1. Evaluated at 0. So let's substitute x1 is to as 0. We have minus 1, 0, 1 and minus 1. So this is the linearized system. Talk about stability, we need to talk about the eigenvalues of A. Right? So determinant of A minus lambda I. This is the characteristic equation. We get we have repeated eigenvalues at minus 1. This implies that the linearized system is stable. Because the eigenvalues are negative real parts. Let's discuss linear system stability. So if we have a system x dot equals ax without any input and we have n states, then depending on the eigenvalues of A, we have various conditions of stability, right? So this is marginal stability. So I'm going to write the eigenvalues as lambda. So if all eigenvalues are have real negative shocks, so this means we'll have to diagonalize this to comment on marginal stability. Jordan blocks corresponding to eigenvalues with zero real parts are of size 1 by 1. Okay, then we have asymptotic stability. All eigenvalues have negative real parts. All eigenvalues have strictly negative real parts. And then we have stable or if at least one eigenvalue has a positive real part, strictly positive real part, or zero. So either it has a strictly positive real part, and if it has a zero real part, then the dimension of the corresponding Jordan block is greater than 1 by 1. We also have uh, another condition on asymptotic stability. So that this is for every symmetric positive definite matrix Q. Symmetric positive definite matrix Q. There exists a solution P to the Lyapunov equation. It is A transpose P plus PA equals minus 4. So given Q, that is symmetric and positive definite, we have to find the P from this equation. And moreover, P is also symmetric and positive definite. So if the solution to the Lyapunov equation P is symmetric and positive definite, then the system is asymptotically stable. Question. Consider the linear system with A equals 2, 1, 0, minus 2. This is a second order system. We can quickly find the eigenvalues, right? This is determinant of A minus lambda I equals 0. Alright, so we have 2 minus lambda, which implies lambda equals 2, and minus 2 minus lambda equals 0, which implies lambda equals minus 2. We have a eigenvalue with positive real part. Therefore, the system is unstable. Since the system is unstable, we don't have to talk about marginal stability, right? Okay. Let's so this is part A, and part B is a third order system. So this is 0, 1, 0, 0, 0, 0, 0, 0, minus 2. We have to talk about asymptotic stability and marginal stability. So observe that this is already in the Jordan form. First, we have this, right? So we have eigenvalues as lambda equals 0, 0, and minus 2. So this is fine. But we have eigenvalues with 0 real part, and the dimension of the Jordan block is 2 by 2. Dimension is 2 by 2. So the system is not marginally stable. Because Jordan block corresponding to lambda equals 0. So, and the system is not asymptotically stable because you have eigenvalues which do not have strictly negative gray paths. So if we had instead a second order system which looked like this 0, -2, 0, 0. So in this case, we have lambda equals 0 and -2. So the system is again not asymptotically stable. The system is marginally stable, right? Because the Jordan block corresponding to 0 is 1 by 1. This is the so the other eigenvalue has negative real parts, and the zero eigenvalue with zero real part has a Jordan block of 1 by 1 dimension. System again, this is A equals 0, 0, 0, 0, -1, 1. So what does this mean? We already have it in the Jordan form. So let's see. Here are repeated eigenvalues at lambda equals -1 and a single eigenvalue at 0. This is not asymptotically stable. But this is marginally stable. Because we have -1 with the negative real part, and this is dimension 1 by 1. So if this is clear, let's move on to the next question. Consider the LTI system. X dot equals -1, 2, 0, -1, and x. So compute P with Q equals -I. So instead of computing the eigenvalues, we now have to compute the solution to the Lyapunov equation. We transpose P plus PA equals -2. Okay. And Q should be symmetric and positive definite. So if Q is -I, this is -1, 0, 0, 1. This plus we need it to be positive definite. So the eigenvalue should be positive. This is so Q is symmetric and Q is positive definite because lambdas are 1 and 1. So let's see if we can get the solution P. P has to be symmetric. So let's see that P is P11, P12, P12 and P22. So we have to find these three coefficients and then check if P is positive definitely. So the first is A transpose B minus 1, 2, 0, minus 1. This is minus P11, then we have minus P12. Okay, then we have PA. Alright. So now let's add these two, A transpose P plus PA. This is minus 2P11, 2P11 minus 2P12. Let me know if there are any mistakes with the calculation. This is 2P11 minus 2P12. Okay. And this is 4P12 minus 2P2. This has to be equal to minus Q. This is minus 1, 0, 0, 1. Okay, so I think we have three equations. The first one is minus 2P11 equals minus 1, which implies P11 is half. Then we have 2P11 minus 2P12 equals 0. This implies that P12 is P11, which is half. And the last equation is 4P12 minus 2P22 equals minus 1. Sorry, this is plus 1 equals 2P22. 3/2. So P is half, and then we also have half here and 3/2. Now let's check if this is positive definitely. So let's see. To check this, we have to compute the eigenvalues of P. This is determinant P minus lambda I. We have half minus lambda, half, half, and 3/2 minus. Minus 1/4 equals 0. Okay, so we get 3/2 minus half lambda minus 3/2 lambda plus lambda square minus 1/4. We have lambda square, and then we have minus lambda 3/2 plus half. minus 2 lambda, and we have plus half. So lambda is if we have 2 plus minus okay. So eigenvalues of P have positive real parts, strictly positive. Therefore, P is positive level. And this implies that the system is asymptotically stable. So note that even Q, that is, you have to choose Q which is symmetric and positive definite. Compute a symmetric matrix P from the Lyapunov equation. A transpose P plus P equals minus. If P is positive definite, the system is asymptotically stable. If it is not, then you cannot conclude anything. I hope that this was clear to you. Now let's move on to the next topic of Vivo stability. This is the fourth topic. Let me check once. Okay, fifth. Okay, so for Vivo stability, so let's talk about linear system. Since we are talking about input and output in Vivo stability, we need the whole state equation, right? Ax plus bu and y equals cx plus d. Okay. So the linear system is Vivo stable and only if the pole of every entry of the transfer function is a strictly negative real part. So we already know how to compute the transfer function of a system, right? This is G of S, Laplace inverse, C S I minus A inverse. Just take B. Sorry, just one second. Okay, and if D is 0, so we can just have a simple case of Laplace inverse of CSI minus A inverse times B. So we're talking about the transfer function because this gives the impulse response. And if the, sorry, if the input is bounded, then to check that if the output is bounded as well, we need the impulse response, right? So the impulse response should also be bounded, or we can also say that in the case of linear system, the poles should have negative real parts so that it decays down to zero. Okay, so let's check. For the system, let's this is question 8. Okay, so let's say that the linear system x equals 0, 1, minus 2, minus 3, x plus minus 0, and y equals 1, 0. The first observation is that a is 0. Okay. I have to compute Si minus a inverse. So this is S plus 3 minus 1 and 2. So this is going to be 1 upon determinant. This is S square plus 3S. And we interchange the entries on the main line. And then this the octile elements to the opposite sides. Okay. C S I minus A inverse. This is 1, 0. Simply S plus 3 and 1. And then this times B would be B is just 1, 0. This means the first integral. This is S plus 3, S square plus 3S plus 2. Okay, so this is G of S. Now let's find out the eigenvalues of the denominator. So this is minus 1, minus 2. So the poles, let's write this down. The system is vivo stable. So note that if you had the same B but different C and B, then the answer could be different, right? The transfer function would have positive or zero real part, in which case the system would not be Levy statement. All right, so this is it for today. If you have any doubts, please go ahead and ask. If not, then you are free to.